Here we'll look at vertical shifts of periodic functions. For a periodic function of the general form y equals a sine t plus k, the absolute value of a is the amplitude, and k is a vertical shift of the function. Let's make a sketch of each of the periodic functions below, and we'll see how vertical shifts work. So the first thing I'm going to do is I'm going to draw the inverted cosine of t graph. And I'll just sketch it lightly because what we want to do is shift it vertically according to the formula. Alright, that is negative cosine t. But our formula says 3 minus cosine t. So we're going to shift it up 3 units. And here, k is 3. Okay, so let's shift it. 1, 2, 3. And this is the function negative cosine t plus 3. The amplitude of the function is simply 1 because the value of a here is negative 1. And the value of k is positive 3. So it's a vertical shift of positive 3 units. Over here I'm going to sketch 2 sine t. 2 sine t is a vertical stretch of sine t. Okay, and this would be the function 2 sine t. Now we want to shift it by 2 units down. Alright, so our amplitude here is 2. So we have a equal to 2. And the a is this number here. And the k is negative 2. The phase of an oscillating function is the fraction of the wave cycle that's elapsed relative to the start of the cycle. Graphed below is just the simple function f of t equals sine t. Some phases of f of t are given for a few different points. Now sine gets started at the origin with a value of 0. And at that time, we see that the phase is 0. When sine reaches a peak, the phase is pi over 2. If sine comes back down to 0 after just achieving a crest, then the phase will be pi. When sine is in a trough, the phase is 3 pi over 2, And then when sine returns to 0 after making that complete cycle, the phase returns to 0 as well. Below is a transformation of sine t. This is sine of 1/2 t. And this is a horizontal stretch of sine t. Find the phase of the function at each of the given points. Okay, so we know the basic shape of a sine graph. It starts off at 0 at the origin. So at A, that's going to be the beginning of a cycle. It's a phase of 0. Then when we get to the end of the cycle at F, that's a phase of 0 as well, because the entire cycle has been completed. So as you can see, it doesn't really matter what the exact times are when it comes to the phase. At D, we've returned to 0, but that doesn't mean the cycle is actually over. This is a phase of pi. We're halfway through the cycle. At B, we're 1/4 of the way through the cycle. So we have a phase of pi over 2. And at E, we have a phase of 3 pi over 2. It's a little bit harder to do C. What phase are we in at point C? Well, one way we can do this is to figure that the phase, so the phase is equal to some fraction of how much of the cycle has been completed out of the total. So even just counting the grid lines here, there are 8 total grid lines. And at C, we've completed 3 of them. So we've completed 3/8 of a cycle, but we need an angle in radians. So we want to multiply by 2 pi. So it looks like we actually have 3 pi over 4 at C.